So I'm going through perfusion, mammalian cell culture for recombinant protein manufacturing. The manufacturing, so so that's how the perfusion system looks like. You have a cell retention device, cell-free harvest, and then there's a bleed. So the most common cultivation, not this. Let us first introduce the basic parameters that describe the operation of a perfusion process. The media exchange rate can be defined either by the perfusion rate expressed in vessel volumes of media per bioreactor volume per day or by cell specific perfusion rate. These are the two uh, exchange rate that you have to consider. Expressed in picoliters per cell per day. Note that the perfusion rate represents the operational volume but does not give any information on the cell density, while the cell specific perfusion rate is the media consumption normalized to the cell density and therefore gives an indication about the performance of the media. So another parameter that needs to be mentioned here is the bleed rate. This parameter corresponds to the cell biomass removed from the bioreactor in order to maintain a constant cell density value equals to the desired set point. Since this stream is wasted with no recovery of the target protein in order to maximize the process yield, it its rate should be minimized. So this is just an extra stream. The performance and yield of a process dependent on the different flow rates. And increased perfusion rate generally enables the generation of more biomass and thus more product. The faster the cell grows, the larger is the bleed rate and the smaller the yield. Stable operation should therefore be defined in a range where the cell density is large enough to achieve an economically viable productivity, but in a state where cell growth is controlled either by nutrient limitation or other environmental factors to minimize the bleed rate. Of course, all these parameters highly depend on the performance of the given cell line that imposes its own consumption and specific productivity constraints. Perfusion rate. Oh, cell retention device for suspended mammalian cells. Existing cell retention devices are based on either cell size or density. They include filters, cross-flow hollow fiber, centrifuges, gravity settlers of different geometry, and acoustic wave separators. Each of them has advantages and drawbacks that are well discussed in the cited reviews. The retention devices that achieve the most attention today are tangential filtration systems such as alternating tangential flow and the tangential flow filtration. Hollow fiber systems, the ADF benefits from a self-cleaning effect induced by the alternating flow. A study from this compares different features of the commercially available ADF and a homemade tangential flow filtration device using the same hollow fibers. Perfusion runs with three operating set points, 20, 60, 40 million cells per ml. In this order were performed and repeated using both ADF and TFF. A reliable retention device should not only prevent cells from leaving the reactor and the harvest stream but also satisfy some important operation requirements. These include avoid product retention, operate for a reasonable range of perfusion rate values, provide sufficient aeration to the cells when preventing harmful shear, operate across scales from process development to manufacturing, and finally guarantee a significantly long operation without failure, thus avoiding, for example, filter fouling. These aspects have been considered in various studies where different cell retention devices have been compared. For example, it was shown that when using an ADF instead of an internal spin filter, the maximum cell density and the maximum perfusion rate could be increased. In the production bioreactor, usually referred to as an N-stage bioreactor, cell culture can rapidly reach a biomass exceeding the system capacity due to nutrient or equipment limitation, where the cell viability rapidly drops. To prevent this, a control on the cell density can be implemented. This way, the biomass is kept constant during a longer production phase. When considering both the N1 and N phase, different strategies can be adopted where batch, fed batch, and perfusion modes can be alternated in different ways. In the following, we review a exhaustive list of recent examples where different approaches have been implemented to control and maintain a stable for a reasonable long time high density perfusion cell culture. Semi-continuous and continuous bleeding were used based on daily cell count or online biomass sensor monitoring, respectively. A daily bleed induces a discontinuous tooth behavior where the cell density increases continuously between two consecutive bleeding points, where it then obviously drops. This method can be used if no online monitoring and control is available. As an alternative, continuous bleed adjusted on a daily basis based on cell count can be used and leads to more stable reactor behavior. This strategy differs from the semi-continuous approach because of the continuous cell removal, but is subject to variation if the cell growth rate changes in time for whatever reason. Dowd et al. Reported 5-day long stable operation states at about 50 times 10 to the power 6 viable cells per ml using an acoustic filter and a CSPR of 0.05 to zero point 0.4 nl cell per day. Reported viable cell densities of 20 to 35 times 10 to the power 6 cells per ml at about 1.4 volume per volume per day using a TFF, using an ATF 90 to 130 times 10 to the power 6 viable cells per ml using a perfusion rate of this. Compared the performance of different processes using a very similar media in order to provide a fair comparison in their productivity, in particular batch, fed batch, concentrated fed batch, and perfusion processes were compared. It was found that the specific cell productivity remains in a similar range for all production modes, and therefore the reactor final volumetric productivity is defined by the achieved cell density for perfusion.